Okay, take a look at your smartphone right now. Have you ever actually stopped to wonder how on earth does a device that's maybe 1 centimeter thick capture 8K cinematic quality video? I mean, think about the sheer physical space constraints here. We're talking about pulling professional grade footage out of an impossibly thin slab of glass and metal that just lives in your pocket. It honestly feels a bit like magic, doesn't it? Well, spoiler alert, it's not magic. It's an absolute masterpiece of modern engineering. Welcome to this explainer. Today, we're going to trace the fascinating journey of light. We'll follow a single photon from the physical world straight through some mind-blowingly microscopic hardware right into the digital realm. And then, we're going to flip the script entirely to see how digital artists synthesize that exact same light completely from scratch. Here's our roadmap for the breakdown. First, we'll look at miniature lenses for mobile. 2, CMOS sensors and Bayer filters. 3, the camera's brain, also known as the ISP. 4, simulating reality in 3D. And finally, 5, cinematic digital lighting techniques. All right, kicking things off with part 1, miniature lenses for mobile and how we go about shrinking the optics. For years, the absolute biggest roadblock for camera engineers was literally just physical space. Because our phones keep getting thinner and thinner, the optics inside have to shrink, but without sacrificing that incredible image quality we demand. Before modern sensors came along, squeezing camera lenses into a phone was a nightmare. They used to be over 1 centimeter thick. But today, engineers are stacking 5 to 6 ultra-thin plastic lens elements in there. Now, you might be wondering, why plastic instead of glass? Well, it's way cheaper, sure, but more importantly, it can be easily molded into these highly complex, bizarre shapes that are required to correct optical aberrations inside such a tiny, cramped space. Moving right along to part 2, CMOS sensors and Bayer filters, basically capturing the light. So historically, in the great battle of the camera sensors, CCD sensors were the gold standard. They had less noise and low light because they used one single amplifier for all the pixels. But, as we know, CMOS totally won the mobile race. Why? Well, CMOS uses separate amplifiers for each individual pixel, which makes processing speeds blazing fast. But the real kicker is the power consumption. It is astonishingly low. We're talking 100 times less power than a CCD. That's literally the difference between your phone draining its battery in minutes versus lasting for hours. Plus, they're way cheaper to make. Honestly, CMOS is the reason mobile photography skyrocketed the way it did. Just take a look at this beautifully complex piece of tech. This is the OV21840 CMOS image sensor. It crams a whopping 21.4 megapixels into its active array. And what's really mind-blowing is the size of each pixel, just 1.2 micrometers. To put that into perspective, that is microscopic. By shrinking the pixels down that much, the sensor captures massive resolution, letting your phone shoot 4K video at 30 frames per second in full HDR. It's just a tiny powerhouse. But here is a crazy caveat. The sensor itself only collects light intensity. It actually doesn't see color at all. And that brings us to the Bayer filter. Think of it like a microscopic mosaic glued directly over those tiny photosensors. It's an array of red, green, and blue color filters on a square grid, usually laid out as half green, a quarter red, and a quarter blue. That specific pattern is what translates the raw black and white light intensity into the distinct red, green, and blue data points we need to eventually synthesize a full color image. Which leads us perfectly into part 3, the camera's brain, the ISP. Meet the Image Signal Processor, or the ISP. This is the hidden, unsung hero of a chip that actually takes all that raw, scrambled sensor data and turns it into the gorgeous RGB images we see on our screens. You can really think of the ISP as a lightning-fast, microscopic photo editor living inside your phone. It decides everything, from how much texture survives in the dark shadows to making sure your skin tones look natural. It is the ultimate interpreter of the physical world. When you tap that shutter button, you aren't just snapping a picture. The ISP instantly goes into overdrive, performing billions of arithmetic operations in mere milliseconds. It's simultaneously managing the focus, adjusting exposure, tweaking white balance, tuning colors, aggressively scrubbing out digital noise, and compressing the dynamic range so you don't blow out the sky while trying to capture a face in the shadows. It does all the heavy lifting, completely behind the scenes. And this is exactly why the ISP is an absolute game changer. If you take a small sensor and pair it with a weak ISP, you're going to get grainy, smeared messes the second the lights go down. But pair that exact same small sensor with a powerhouse ISP, like Qualcomm Spectra or Samsung's Exynos, and suddenly you get a clean, sharp, highly readable image. These processors are the actual secret sauce behind things like computational night mode, real-time video stabilization, and capturing that massive 8K video. They literally shape the light. Okay, let's take a quick breather. We've spent this whole time talking about how physical lenses and microscopic sensors capture real-world light. But I want to throw a curveball at you. What if the camera doesn't actually exist? How do we replicate this insanely complex physical process when we are building completely digital virtual worlds from scratch?
That brings us to part 4, simulating reality in 3D. Welcome to the virtual stage.
So, stepping onto the virtual stage, digital artists actually face the exact same lighting and rendering problems that those smartphone engineers do. Take a 3D architectural fly-through animation, for example. It usually unfolds in stages. You start with a map view to set the context, then swoop into an aerial bird's eye view, transition into a fly-through of the surroundings, and finally, glide right through the building's exterior and interior. Unlike flat 2D graphics, adding that third dimension of depth creates this incredibly realistic portrayal that mirrors real life, giving buyers or investors a totally immersive experience.
And that leads us to our final section, Part 5, Cinematic Digital Lighting Techniques, or as I like to call it, faking the physics.
To keep these digital models from looking flat and boring in software like After Effects, artists literally have to fake the physics of light that our phone sensors capture so naturally. And how do they pull that off? They use the classic three-point lighting setup. Step 1 is the key light. That's your primary, brightest spotlight hitting the front of the subject. But naturally, that creates harsh shadows. So step 2, the fill light. This is a slightly dimmer light placed on the opposite side to fill in those shadows and balance the exposure out. And finally, step 3 is the backlight, placed behind the subject to catch the edges, giving it a subtle rim light that separates it from the background and adds that true cinematic depth.
Now, manually managing all these individual spotlights in a 3D space? Absolute headache. So 3D artists use this brilliant trick. They rig their virtual lights to a 3D null object. By parenting the key, fill, and backlights to a single invisible point in the dead center of the scene, they build a custom light rig. Then you just rotate that one null object, and the entire complex lighting environment rotates seamlessly around your subject. It generates these highly dramatic, cinematic looks instantly, without having to manually tweak every single digital bulb. It is just incredibly efficient. So we've seen how mobile phones use microscopic plastics, CMOS sensors, and hyper-advanced ISPs to interpret physical light. And on the flip side, we've seen how 3D artists use virtual light rigs to synthesize that exact same reality out of thin air. Today, it all just kind of blends together into the media we consume every single day. So the next time you're scrolling and you stop on a truly stunning cinematic image, I want you to ask yourself, was this captured by a physical lens and a tiny processor in someone's pocket, or was the whole thing entirely synthesized on a virtual 3D stage? The line is getting blurrier every single day, and honestly, I think that's absolutely fascinating. Thanks for exploring this explainer with me.